In this video, we're looking at implicit differentiation. First, we'll start off with a chain rule. If I want to differentiate something like x squared take 3 to the 6, normally the notation is d by dx in front of all that. And it's going to equal, well, 6 lots of x squared take 3 to the power of 5 times the derivative of the stuff inside, so that's 2x. Now, if you have something like u to the power of 6, and we want to differentiate that, thinking u is like a function of x, well, you would get 6u to the 5, and you would have to times it by du dx. Similarly, y to the power of 6, if we wanted to differentiate that with respect to x, you would get 6y to the 5 times dy dx. And this is going to be like the core thing we do in implicit differentiation. Sometimes that doesn't even have to be x. You could have like t there, and then you would have a t there, for example. Okay, so let's do a normal derivative question. Find that slope. So what we want to do is differentiate both sides, essentially. So that's going to be 2x there. The plus 1 just goes away. And then the derivative of y, it's going to look a little bit weird here, but the derivative of y we can think of as just 1 times dy dx. This is where the whole dy dx notation comes from. So it's a very weird way of me writing this, but essentially we get the same answer. Dy dx is 2x, and then we could say something like add x equals 1, dy dx is 2 times 1, so that's 2. And just as a little example of what that means, we can look at the y equals x squared plus 1 function, and you can see that at x equals 1, the slope is about 2. It's going up 2 for every 1 it goes across. Okay. We got this circle here. So we need to find the derivative. Now this is where implicit differentiation actually gets useful. X squared goes down to 2x. Y squared goes down to 2y, but we're differentiating with respect to x, so we have to times by dy dx here. And 1 will go down to nothing. So if we rearrange this, we're going to get 2y dy dx equals negative 2x, or in other words, dy dx would be minus 2x over 2y, so it's just minus x over y. Okay. Now let's do some examples of actually getting slopes. So we have some key points on this circle. So for example, this point up here at the top, this is at 0, 1. And so dy dx for this bit would be minus the x value over 1. So that would be 0. And I'm hoping we can see here that the slope at this point at the top is actually flat and is 0. If we have another point, for example, this one, so this is at 1, 0. So dy dx here would be the x value, so minus 1 over 0. Remember, there's a minus sign in the whole formula. So that would give us undefined. I'm hoping that we can agree that the slope here is undefined because it's going straight up and down. This point up here, if you're comfortable with trigonometry, this is 1 over root 2 and 1 over root 2. Some people like to write this one as root 2 over 2 and root 2 over 2, just depends what you're more comfortable with. But at any rate, the dy dx value is going to be the x, so, well, negative of the x, so negative 1 over root 2, all over 1 over root 2. So that is minus 1, just like that. Okay, and I'm hoping we can sort of see here that the slope is about minus 1. And you can get the slope at any point using this method. Lucky last, we'll just get dy dx for this function. So cos of x is just going to go straight down to minus sine of x when we differentiate it. xy, we need to use a product rule. So u would be x, v would be y. U would be 1 because we're differentiating with respect to x here. And v dash would be 1 times dy dx. Okay. So this is going to be, I just write out u dash v plus uv dash. So minus sine of x is, yeah, that should be u dash there. So this is 1 with y. And then we're going to get x with dy dx. So minus sine of x is y plus x dy dx, and then we can sort of rearrange this for dy dx equals. So let's look at maybe taking y. So minus sine of x, take y. is x times dy dx, and then we can divide out by x. So dy dx is going to be minus sine of x take y all over x. And we can plug in any x, y coordinates, so we have to get the slopes there. Just in case you're curious about what this function looks like, it is very fun. Implicit relationships can look pretty wacky.